other questions for Andres, please post them in the chat and he will reply to them. So now it's my pleasure to introduce you to Nanda Rea, who will speak about compact objects and the Milky Way. Nanda is my colleague at the Institute of Space Sciences, and she studies compact objects and theoretical simulations of isolated neutron star population. She has an impressive publication record plus an ERC Consolidator grant, and she has received international awards, among them the National Award for Young Researchers from the Catalonian government, and also the Prize for Female Scientists from the Real Academia de las Ciencias. So it's an honor for me to give her the word, and the floor is yours.
Thank you very much. Thanks for the invitation. It's very interesting to be here. I'm already learning a lot, actually. Let me start this. I'm probably the least expert in machine learning among the whole speaker. We just started to work on this, and actually we just published a few things. So we have a project that I will explain you at the end. And I would say that probably compared to solar physics and to galaxies and galaxy evolution and cosmology, the compact objects, it's one of the fields where machine learning it's less developed and less used, but still this is starting, and I will show you at the end a few examples on how this could actually help this kind of science. So given the broad audience, I actually planned the presentation and the 15 minutes to start to explain to everybody what compact objects are, and because I didn't know, maybe there are people from institute which are not even astronomy. So, and then we'll get two examples more in detail on where machine learning has been applied. One from in my group, especially Vanessa Graber and Michele Ronchi, which are working on this, and another group in the UK. Okay, compact objects. All astronomers do know, but non-astronomers maybe not what they are. They are the leftovers of the end of stars. So they are dead stars. Mainly I will speak about neutron star and black holes and things applied to those. But there is a lot also in white dwarf, but just had no time to cover everything. So after the supernova, after the evolution of massive stars, we have supernova explosion, and then what is left is usually one of those very extreme dead stars with a lot of gravity and a lot of usually emitting in X-rays or radio bands. Neutron stars, one solar masses in 10 kilometers radius, very strong magnetic field and very high rotation. Those are, we know plenty of those sources in our galaxies. Why they are important? Because they are the most densest object we know of. They have the density of a nuclear atom. They are important for several points of view by theoretical physicists, particle physicists, astrophysics, nuclear physicists. So there are every people actually look at them from a different point of view and has a different laboratories. But how many we know? We know more or less, I'm sorry, this wasn't supposed to go this way. We know more or less, no, this is not working, I'm sorry, not sure why, doesn't matter. We know more or less 1,000 of them. They were discovered 50 years ago. The first one, we know thousands of them now. So the numbers is such that now we can really do population studies. And this is where actually machine learning started to come to work. They are very important because they are extreme, very extreme laboratories. They are the densest rigid body we know in the galaxy. They have, as I said, the nuclear density. They are the fastest rotating rigid body that we know of. So imagine the mass of the sun in 10 kilometers rotating at 1 millisecond. So the tangential velocity that they have, so the velocity of the surface, a part of the surface actually feels is 50% the velocity of light. So this means that there are so many gravitational GR and general relativity and special relativity effects that we have to take into account when we study this source, that this is not the case for any others. They are of a lot of use, even if for the international system, they are the definition of circle. The most circular thing that we know of is actually the orbit of a binary neutron star, for which they are so precise clock, we can measure their orbit with a precision of 1/10 human hair. And so this is round at this precision. So they have a lot of, the fact that they are perfect clocked and very dense and stable, they make them fantastic laboratories for many things. They are the most stable clock we know of. They are not the most precise. Now we have optical clocks, quantum optical clocks. We have other clocks which might be slightly more precise than a pulsar, but they are the most stable. They can be as precise for mega years. And this is also what makes them very interesting. They are the most magnetic things of the universe. As you can imagine, when you put a plasma and you want to study the physics of something embedded in 10 to the 15 Gauss, our physics is completely different than what happened in something at 1 Gauss or the Earth. Because as you imagine an atom, an hydrogen atom in 10 to the 15 Gauss has not the shape of a Bohr atom, but is actually like a spaghetti. So there is a lot of physics that actually we need to test and learn from observing those sources. And they are the most precise after gravitational waves now, tests of general relativity. We can measure the orbital decay of those binary systems via gravitational waves with a precision of 10 to the -2, which is extremely important also for testing other theory of gravity that should somehow explain this. It's not finished. They are gravitational waves detectors. So we can use those clocks to detect gravitational waves. And this is also something important for the machine learning side, but I don't have the time to speak about it. But anyway, so this is extremely important because they are a detector. We can use those clocks, observing in radio those clocks. We can somehow try to measure the gravitational waves from merging of supermassive black holes. We can measure masses of planets with pulsars because they are so precise that their arrival time it's actually delayed by the gravitational dwell of our own solar system while arriving. So this means that we can measure perfectly which are the masses of the planets, the very massive one, the small one, no, not yet at least, for using those systems. And we can also use them as GPS systems to travel out of space. It's the only way we can, in the future, actually live our solar system and have a GPS in work using those clocks all over the galaxy just as a GPS. Okay, so just to give you an idea why it's important to study those objects. Black holes, the other compact objects, though they are also extremely interesting, also for cosmologists, because they have, we have primordial black holes. We have black holes in most of the galaxies, central supermassive black holes, so they interact with the evolution of the galaxy since the very early ages in the universe. So they are extremely interesting for several kinds of science. What do we know? So the first black hole discovered and classified was, again, more or less 50 years ago, which is Cygnus X1, which is an X-ray binary in our galaxy, a very bright one, that was the first somehow being accepted to be a real observed black hole. Since then, we know many in our galaxy and other galaxies. For example, on the left, which is a very famous image that I'm sure everybody knows, which is the M87 image of the Event Horizon Telescope, where with the polarization, where we could really measure the effect of the disk and the gravity close to the supermassive black hole. On the right, you see different masses of black holes discovered by gravitational wave mergers, and also in violet black holes, which are instead isolated and are in other galaxies that we can measure via observation in several bands. How do we observe these black holes? They are usually either in stellar mass black holes, so with a companion star. So what we see is the X-ray or radio or sometimes optical emission of the accretion from material from a massive star or a low mass star to the black hole. They form disks, they form jet, they can accelerate very powerful jet that can be observed in radio in many images with many radio interferometers. We see them also as active galactic nuclei. This is actually our own, for which we see stars around which orbit around the black hole. And we can measure the mass of the black hole from the stars going from the orbits of the different massive stars going around. And this is just one of the supermassive black holes. There are active galactic nuclei in most of the galaxies we see, and we see them very far away, mainly in the X-rays, and sometimes in some cases even in the gamma ray band. We also see tidal disruption events, if I'm able to change. Yes, tidal disruption events are instead black holes that at certain point might interact with a star, usually, and it's up. It's completely the star. So we see them getting very bright, and then their luminosity decay. And from modeling this, we can get a lot of information on the kind of mass of the star and the mass of the black hole and many other things. So this is more or less the scenario in which the kind of compact objects that we see in our galaxy, and in some cases, especially for black hole in external galaxies. Now, I will show you now just two cases of application of machine learning. As I said, this is probably one of the fields where this has started later, mainly because it doesn't imply huge amount of data or catalog or doing a catalog of these, or having to recognize different classes from a huge amount of images. This is why this came probably late, but this will be very useful very soon. That for SKA, for example, that we will have a lot of radio sources, we will need to distinguish what they are, or the Vera Rubin telescope, or for many other kind of science. So one of the example in which this is what we are doing, we are trying to do, especially Michele Ronchi and Vanessa Graber, which are the real expert, rather than myself, which I'm the least expert in the group. What we try to do is to apply machine learning to a population study. So we took the dots that you see here. This is our galaxy, Ryan deck simply, and all the dots and you see and the lines are pulsars detected in our galaxy for which we have a proper motion. So we know the lines that you see are where they are going, and the length is depending on their age and how fast they are in their age. So what we want to know, because we see our galaxy now, so we have a picture and we can measure more or less 200 of those proper motions so far. SKA will measure plenty of them, but so far we have more or less 200. What we want to know is which is the distribution at birth of those pulsars, where they're all born in the arms of the disk, at which height from the galactic plane, how they move, and which is the distribution of their proper motion, because this will be connected to the explosion of massive star. So which is the kick velocity that then the supernova can give to a pulsar at birth. This is connected to the distribution of proper motion that we see from this star. So this is the first work that we did in this direction. What we did, it's taking this is somehow the data that we have, those 200 sources, and try to see if with machine learning, we could reconstruct somehow the distribution of height at birth and proper motion at birth of the population of pulsars. So we did we built a physical model where we have put our galactic dwell, we have put this different distribution of kick velocity for pulsar compared to what we see. We put pulsars in different configuration in the arms of our galaxy. So with it, we put all the physics that we think it's in place, and we generate different maps given those different parameters. And what we did after this, which are the density map and velocity map, we've built a convolutional neural network which were trained on those maps to try then to learn which is what can we get from the data we have now, and what we will be able to get when we will have 2,000 of those measurements or 3,000 of those measurements. How well we will be able to constrain, for example, the distribution of kick velocities of pulsars. And we actually we found that this is something that it's very promising. Definitely, we cannot have a very precise distribution right now because we only have 200 sources, but we will with SKA, where we will have almost 2,000. And this is just a simulation on how the galaxy will look like with all the pulsars going all over the place when we will have 2,000 of those, where we will be able indeed to constrain the kick velocity at birth for those sources. Next step is to make this even more complicated, and we are, especially Vanessa and Michele, we are already working on this, which is adding more models. So adding, for example, how spin period distribution, magnetic field distribution, and what we want to do is to constrain the physical properties of the whole neutron star population at birth when they are born. So to have an idea on which is the magnetic field distribution that we might have, period distribution, luminosity distribution, and all the properties of the population itself. This will probably be very difficult to be constraining right now, where we have only 3,000 sources, but in 5-10 years, we will have 10 times more of this because of the upcoming instruments. So then having this in place is going to be very important then. Black hole, this is one of the example in which machine learning has been applied for black hole studies, one of the few, there are not many yet, but this is growing a lot. One example is indeed to do classification, which is one of the most powerful tools that can be done. This is an example of a work where from a certain catalog of archival X-ray data, they try to train a random forest classifier to understand if the strong X-ray source they were seeing in this large survey was a neutron star binary or a black hole binary. The two things differs mainly in the spectrum that they have in an X-rays. So this is why, which is here, it's modeled as hard color. And so they took all the observation that they have in the catalogs, which you see in the left. Those are in orange are black holes, and in blue are neutron stars. Those are all in our galaxy, most of it. And those are the number of observations that are available in this big archive of X-ray observation. So they found out that with number of observation, which are between 100 and 1,000 observation for a single source, they predict a probability of correct identification, that is the plot on the left, of more than 90%. The fewer the observation, of course, less accurate this is going to be. And this is extremely important work. I mean, it's one of the first where machine learning is used to classify things in the compact object world. This is very common in galaxies, of course, but it's just starting in our field. And indeed, this is going to be very useful for a lot of large surveys where we will have plenty of X-ray sources and nobody will be able to get one by one each of them and look at each of them one by one, which is probably how the people in doing galaxy surveys does already, but we never did so far. And this is an example that actually this might work, and we can distinguish black hole binaries pretty easily with with a reasonable number of observation of the field. That said, just to thank all the people in the group, especially Vanessa, Michele, and Celsa, which are the one actually working on machine learning in our group and doing most of this work. And thank you very much for the invitation.
Thank you very much, Nanda, for this very nice review and the introduction on compact objects. If there are any questions from the audience, please post them in the chat. Otherwise, I will, Mark, go ahead.
Yes, hello, Nanda, thank you very much. I have just a general question. So it's interesting to see how machine learning has penetrated differently in different fields. And so you think in your case, it's starting only because it hasn't, let's say, penetrated that much because you don't have that big data volumes, or it's because you don't need it because you understand, I mean, the physical models that you use are not that complex, so that you don't need really a data-driven approach. So which one is it that it's, preventing it?
I think it depends on the case. Both things can be true. So on one side, we don't have yet such a huge data volume that, for example, galaxy surveys might have. So in many cases, we can really go one by one and look at stuff. Now, this is, people already started to see that with the eROSITA or with Future SKA, with many surveys, this is not possible anymore. So this is why there are several groups that just started to enter in this machine learning from a, let's say, a cataloging point of view. There is another more from a population study point of view. So there are several things in population study, both in black hole binaries or isolated, where so far we didn't have much objects. So we thought that the physics that we had was simple enough to do the things analytically. The more you observe, the more data and information you get, you realize that the few parameters that you think that were the important ones are not enough. So your problem starts to become a multi-parameter problem. And when the parameters are very big, the degeneracies are very big, and it's very difficult to constrain the physics when you have so many degenerate parameters. And in there also, this is another place where people are starting to use machine learning. When they have many parameters, they don't know which one it's actually more important or driving most of the physics, because some of them can drive your results in the same direction and you don't know which one is actually applying. And this is where another part of the community, the more from the theories and population side, are actually starting to entering the machine learning, because to hope that the machine blindly will understand which is your parameter constraints, I think. I would say this is more or less the...
Thank you. Yeah. So it's it's probably therefore just a delayed curve, let's say.
I think so. I think so. Yeah.
Yeah, as a kind of similar question, I think you partly answered that, but what would you ask machine learning? What would you like machine learning to do for your research in the next years?
The point is that as a physicist, I mean, as physicists, we are very attached. This is what I understand from myself and the people, physics that work with me. We are very attached to the meaning of an error. So you have a measurement and I want my error. How much can I believe this? And this is something that sometimes with machine learning, it's a bit tricky to really know which is the error on your measurements. How much can I believe this, you know? And I think this is something that, of course, there are a lot of methods, there are a lot of things that has been developed. Many of them I don't even know because I'm just starting this. So, but this is something that for many people, which are somehow old physicists, used to their handy, even numerical simulation have problems in this sense sometimes. It's something that it's difficult to live this background. So should I believe a black hole machine that I don't even understand what it's doing, you know? And this is complicated, but I mean, it's clearly that it works. And this is why people are just starting to using it, yes, I would say.
I totally agree that uncertainty estimation is something that we should definitely